All right, welcome everyone. We have another GoLab talk for all of you Govers out there. Right now, our talk is going to be accelerating developer velocity, building an API management platform in Go. This talk is presented by Tejaswi Agarwal and Rohit Patali. So I'll tell you a little bit about them before we start. Tejaswi is an experienced software engineer in building large-scale reliable systems across organizations. He is actively building the next-generation API management platform at Uber that power all Uber trips globally. He is an active contributor to open source technology and strongly believes in removing developer bottlenecks to improve developer velocity at engineering organizations. And before Uber, he was developing key features for bringing the Oracle database to the cloud. And Rohit, on the other hand, is a senior engineer on Uber's Gateway platform team. Over the last 3 years, he has helped build the Uber's API gateway from the ground up. He led multiple large-scale projects to safely migrate 1,500 plus APIs from the Node.js legacy system and helped scale it up to 500K QPS. So about this talk, it's all about growing and scaling engineering organizations and how it's hard on the developer productivity. In this talk, they'll focus on the key learnings from building the next generation API management platform at Uber. In its first generation, API management was a single repository with thousands of engineers making code changes to interact with the 3,000 internal microservices. This led to bottlenecks in code reviews, bugs which affected trips globally and caused large-scale outages. In this talk, they'll review the lessons learned from rebuilding this first-generation system into a fully automated API management platform in GoLang. So the automated API management platform provides an ability for developers to ship quickly, with automation handling everything needed to write an API, testing and making it to production. They will cover the lessons from the large-scale migration, migrating 1,500 APIs internally to a new system. They'll talk about centralized versus decentralized migration techniques, what works and what does not. It's like changing the tires of a moving F1 car. So everyone enjoy the talk and then stay tuned for the end. We'll have a live Q&A with our speakers. And I just want to remind everyone gently that if you do have questions to ask, please ask them in the Q&A chat instead of the room chat. The Q&A chat is the one with the question mark icon. So that's just to keep things organized. So thank you very much and enjoy.
Hello everyone, I'm Rohit.
And I'm Tejaswi, and we work at the API platform team at Uber.
Today we are here to talk about the API management platform at Uber built in Go. This platform helped us accelerate developer velocity and improve resiliency of Uber's products. Here's the agenda for our talk today. First, we'll introduce what is an API gateway. Then we'll discuss the high-level architecture of the gateway at Uber. And then we'll discuss the challenges encountered while managing and maintaining the gateway. We are calling this iteration of the gateway as 1.0. Then we'll go into how we redesigned and re-architected the gateway in Go for scale and velocity. We are calling this iteration of the gateway 2.0. Then we will also talk about migrating Uber's entire production traffic from gateway 1.0 to gateway 2.0 safely in the migration plan. And then we will revisit the challenges and see the improvements made by moving to Gateway 2.0, and finally, the learnings that can be more widely adopted from this redesign and migration. A gateway exposes APIs to mobile that act as an interface for applications. The backend services evolve, they are updated and rewritten constantly. At Uber, an average half-life period of a backend service is only 18 months. But mobile apps usually trail behind the backend changes, sometimes by several release cycles. This is especially exacerbated by the need to support several versions of the same mobile app in the wild. In some cases, we still use the same mobile APIs for a lot of our apps that were built 4 or 5 years ago, even though the backend has been rewritten and may expose a slightly different interface. The API layer helps us abstract the backend services so that the mobile apps and the backend are decoupled and can evolve independently. Here are some of the features the Uber's API backend provides. Data validation. The way this works is that every service at Uber has a schema for the APIs, and we use Thrift Ideal for our schema definition. The gateway exposes HTTP interface to mobile and performs validation of the incoming and outgoing payload based on the schema. This ensures that mobile apps don't crash due to incompatible payload. Data transformation, just like the gateway, data transformation, just like the gateway, the backend service have their own Thrift Ideal, which may have different fields from what's defined in the gateway API. This is because the backend evolves over time and may be exposed to multiple different services internally. The gateway layer performs transformation of the incoming payload to match with what is expected by the backend service. Similarly, it also transforms any outgoing payload to match with what is expected with the mobile app. Protocol transformation. Almost all of Uber's backend service expose T-channel interface, which is Uber's open source RPC mechanism. So the gateway layer translates the mobile's HTTP call to the backend T-channel call. Also, the gateway being the central place to all of mobile's traffic, it is a great place to implement common mobile-facing concerns such as rate limiting, payload enrichment, localization, so that every internal service doesn't have to implement these. Observability. The gateway provides logging and metric dashboard, which is a convenient place to triage the impact of an outage from the customer point of view, since it's the central place for all of mobile traffic. At Uber, we auto-generate alerts for latency and increased error rate for these APIs, which automatically page the owning product team. We also provide distributed tracing using Yagar, which is a CNCF project started here at Uber. And security. Security features such as authentication and authorization are implemented at the gateway so that internal services do not have to worry about these concerns for external calls. We also provide a data pipeline through which the product teams can look at long-term trends and user behavior. Now, let us look at some numbers to understand the scale of Uber's API gateway. Uber currently has 1600 plus endpoints exposed in production, serving about 500,000 QPS. Over 1300 engineers from various product teams have used the gateway to launch their features to our apps, making approximately 20 changes a day. This stat is just to highlight the rate and the scale at which changes are being made to the gateway every day. The gateway also requires 100% code coverage. It has currently 50,000 unit tests that run on every change set, and the gateway provides an uptime of 99.99%. Here are some of the popular Uber apps that you may be familiar with or may have used recently, whose entire traffic is routed through the Uber API gateway. Next, we'll look at the high-level architecture of the Uber's gateway in its first generation. The gateway serves as the main entry point to the internal backend infrastructure, but is just another service within the Uber backend ecosystem. There are a few other infra components that come before the gateway and deal with SSL certification validation and other low-level network operation, which are outside the scope of this talk. The Gateway 1.0 was a Node.js application that is deployed as a separate deployment, each serving a specific set of APIs. For example, the Gateway Group 1 depicted here may only serve traffic related to user profiles, and Gateway Group 2 here may route traffic only related to maps or routes, just as an example. Some of the reasons for maintaining separate deployment groups were outage mitigation. If a broken commit had to be rolled back, we can just roll back the deployment that is serving the API instead of rolling back everything. As we saw the pace at which changes are being made earlier, it was important for us to be able to move forward or backward relatively quickly. Also, for ease of management, some of the deployment groups were directly managed and deployed by the product teams, though the code repository itself was owned by the central team that performed all the code reviews. And also for horizontal scalability. Each new API required more memory for storing API schema at runtime and performing data validation at runtime as well. It was easier to scale horizontally on our compute cluster than vertically. This gateway architecture was originally built in 2014, and it helped Uber scale from a single monolith to 2,200 microservices until the end of 2018. However, there were some challenges over time with this architecture that we'll talk about next. Deprecated Node.js version. Uber as a company had moved away from Node.js, but it was among one of the bigger services still implemented in Node.js, leading to a learning curve for new engineers, poor developer velocity. A big aspect of moving fast as a company is to launch new features quickly. Making an API change would cost an engineer around 24 engineering hours, given all the custom framework and the learning curve. The service was deployed once a day, so missing a deploy train caused additional delay. With 25 commits a day, the centralized team could only provide a 24-hour code review SLA. Overall, a simple change that required a couple of review cycles could easily take 1 week to go to production. Hard to enforce API standards. Given the number of engineers making the change and the pace at which it was being done, it was really hard to enforce the same coding standard across the board, leading to code quality concerns. Unclear abstraction. There was no clear boundary between the gateway responsibility versus the domain logic, and sometimes it was just faster to write the entire business logic for a new feature in the gateway rather than spinning up a new service. Runtime performance. Node.js runtime does great for I/O, but over time, more and more CPU-intensive domain logic was added to the gateway, leading to bloat and degradation, and lack of platform robustness. Due to Node.js event loop-based runtime and previously the code quality issues mentioned, oftentimes worker crash from an uncaught exception in one feature caused an overall request from that worker to be dropped, leading to frequent rollbacks and increased on-call burden. Next, we'll look at a live feed of the Gateway 1.0 prod environment that we have prepared for you today. This is obviously an exaggeration. It is important to note that this architecture and its flexibility is what helped Uber's business to scale from hundreds of trips every day to tens of millions of trips every day, and also quickly expand into new geographies. But it was increasingly hard to see how this architecture would continue to serve us in an ever-increasing product scale and demand. This got us to start thinking about how we could make platform experience better, improve developer velocity, as well as better support the scale and reliability. This brings us to Gateway 2.0, which is a ground-up redesign and re-architecture of Uber's API management platform. Some of the highlights of the things that we built include a self-serve user interface for engineers to configure their endpoint, an opinionated code generation framework for generating API code from the aforementioned configuration, a robust runtime to provide various common gateway functionality, and a mechanism to safely migrate and roll out or roll back live production traffic. Let's start by looking at the self-serve UI. The self-serve user interface is the main entry point for when the user wants to create an API. The UI walks the user through a step-by-step process to create a new API. This is where the user configures their API schema using the Rift IDL. Also, this is where they will add one or more reusable components such as authentication, rate limiting, etc. to their API. Select the backend service this API needs to call and configure timeout, retries, and circuit breaking. perform various transformation and enrichment logic to map the fields from the API schema to the backend schema, and configure ownership and alerts for this API. The user is able to go back and resume from where they left off in a previous session. And once done with the flow, a code review is created on behalf of the user and is assigned to their team. This is a big step towards decentralizing the code review process and removing the major bottleneck with the centralized team-based review. This is possible because the change is only configurations that is made from the UI, and sufficient guardrails are put in place that prevents this from breaking the platform itself or other endpoints. Additionally, there are various validation done through the UI as well as the CI test job that run against the generated code review that ensures that the user configuration will are correct and do not result in breakages. Once the code changes are approved and submitted, the endpoint is live with the next deployment. The user may follow a similar process to change one or more things about their existing API, and the UI also conveniently links the auto-generated log and metric dashboard for the given API. Let's take a moment to look through the video to get an idea of what this process looks like. So this is the step-by-step process. These are the middleware. And next, this is how you will go to an existing endpoint and edit any aspect of it. Anyway, next we'll look at how the user configuration translates to the generated code. At the core of the new system is the code generation framework. The framework takes the user configuration provided through the UI and the default platform configuration such as retries, timeouts, circuit breaking, etc. and generate the API code at build time. The code generation is done using Zanzibar, an opinionated framework built in Go and is open sourced on Uber's GitHub. Zanzibar generates code based on the template for the API and the backend client. The templates are hydrated based on the protocol selection, that is HTTP or T-channel, the Thrift ideal schema, and other user-provided configuration through the UI. We also generate all the glue code to map the API request response struct with the backend request response struct, perform any transformation if the field names do not match, and wire all the endpoint together in the main package that has the main function. This is all packaged together as a deployable binary. The actual binary is almost completely made of the generated code. The generated code is consistent and reproducible with each run of the build process, and the user is not expected to write any code. The generated code is committed to the mainline branch of the repository following a commit of the user configuration. Given the fact that we have 1500 plus APIs and 300 plus backend client, we have especially tuned the generation process to detect the changes and only regenerate new code based on those changes. Next, we'll take a look at what happens at the runtime. Within the lifecycle of the request, it flows through the following components: middleware, data validation, endpoint handler, and then the backend client. All the components in the request lifecycle are implemented as a stack. Each of the components operate on the request object on the way in, and the same components are run, but in the reverse order, on the response object on the way out. The middleware layer is an abstraction that implements composable logic before the endpoint handler is invoked. The middleware implements cross-cutting concerns such as authentication, authorization, rate limiting, etc. Each endpoint may choose to configure one or more middleware. In addition to the optional middleware, the platform includes a set of mandatory middleware that are always executed for each request. If a middleware fails execution, the call short circuits the remainder of the stack and the response from the middleware will be returned to the caller. The next step is the endpoint handler. The first thing in the endpoint handler is the deserialization from JSON to the Go struct. Then we perform data validation, that is check if all the requests conform to the correct type from the schema and make sure that all the required fields are present. Also perform any payload transformation and convert the endpoint request object to the backend request object. When operating on the response object, the endpoint handler converts the backend response object back to the API response object, perform any validation on that, and then serialization of the payload. The client performs a request to the backend service. The clients are protocol aware and are generated based on the protocol selected during the configuration. The internal functionality of the client, like request response transformation, circuit breaking, timeout retry, deadlines, error handling, etc., can be configured through the UI. Next, I'm going to hand it over to my teammate Tejasvi, who will talk about the technology we built for migrating and the learnings from the process.
Thank you, Rohit. In this next section, we will talk about how we migrated Uber's traffic from Gateway 1.0 to Gateway 2.0 safely and securely. This was an uphill task that took us 18 months of effort by multiple teams within the company. When we started the migration, we built a plan along with the various product teams. This was a decentralized migration where individual teams would be performing the migration at their own pace. As a platform team, we enable product teams to migrate by providing them with a centralized migration Slack channel. On this channel, product engineers across the company could post their technical questions that would be answered by our team. Within each product team, we created champions that would own and drive the migration for their organization. They would also become the point of contact for migration-related questions. This concept helped us scale and also establish clear ownership for tracking progress and checking in about blockers. Once the logistics was established, we built the technology required to migrate safely. This was possible by providing a framework to shadow production traffic and compare that to the new system. After verification, the next important step was the rollout. Our UI had a built-in mechanism to perform slow rollout to the new system, gated by feature flags, and also provided a mechanism to quickly switch back to the old system in case there were any issues. Along with this, we provided engineering training, extensive documentation, and tutorials that engineers could refer to before and during the migration. Here, we discuss a platform that we built for the safe rollout that engineers use to compare the data being returned from the old system and the new system. As you can see here, when a request arrived to Gateway 1.0, it followed the usual production flow and the response was sent back to the mobile. The response is also replicated to a shadow service backed by Redis. For all production traffic, we send a shadow request to Gateway 2.0 and fetch the corresponding backend response from the Redis cache. Both Gateway 1.0 and Gateway 2.0 responses are then fed into a log comparator service. The log comparator would compare the responses and provide a visualization of the mismatches. The Redis cache here enabled us to build this shadow pipeline for both read and write traffic. The gateway itself is a stateless system. We don't send read or write traffic twice to any of the backend services, as this would violate their consistency guarantees. We built this platform inside of a feature flag that helped us control the percent of traffic being rolled out to shadow or any of the old and new systems. This system helped product teams establish confidence and safely roll out their changes. Based on the shadow system described earlier, this UI here helps an engineer roll out their API from Gateway 1.0 to Gateway 2.0 safely. The dashboard has features to send a percent of shadow traffic to Gateway 2.0 and then monitor their rollout through mismatch logs. You can also monitor the latency of your API in the two systems and check for any performance issues before the actual production rollout. Once an engineer is confident that their shadow rollout of their API changes are safe, they can proceed to incremental production rollout. Incremental production rollout starts directing production traffic to Gateway 2.0 as seen on the left panel above. A thin routing layer that sits before Gateway 1.0 and Gateway 2.0 controls the rollout percent to each system. This shadow traffic system enabled us to completely switch a Tier 1 service running in production. In this section, we will revisit some of the challenges that we faced with Gateway 1.0 and talk about the results from migrating to Gateway 2.0. Go and Java are the two standard languages used at Uber. There are centralized teams that develop and maintain tooling and libraries to help improve the language adoption. With Gateway 2.0, we were able to standardize our API gateway platform to use Go, which is widely adopted at Uber. This helps us focus on our platform instead of building tooling for the language that was previously the case with Node.js. With the widespread adoption of Go, including open source framework like UberFX, which you'll hear soon about in another session, it was very easy for developers to onboard to the new platform. We heavily use Go templates in code generation. Our reflection-based marshalling and unmarshalling of payloads was really fast in Go. Overall, we have been really satisfied with the runtime performance and manageability of our platform in Go. Our developer velocity went from 24 hours to 45 minutes to make an API change. This was possible because of decentralized code reviews, automatic API code generation, and developing an easy-to-use user interface. Today, to write a new API, an engineer does not need to write a single line of code. It is managed from the user interface and backed by the code generation framework. On average, we see about 20 API changes being made on our platform every day. When we see the results, Gateway 2.0 is like giving ourselves 60 engineers every year in saved engineering time and effort. This was a pretty significant shift in developer velocity. This does not include the wait times for code reviews by a centralized team. Gateway 2.0 is completely CI/CD, so new API changes make it to production within a few hours. Due to this, there are no more missed deployment trains. With Gateway 2.0, we were able to create a standardized platform that had built-in functionality for alerts, metrics, and all the different observability. Our code generation framework is open source. You can read more about it on github.com/uber/Zanzibar. Since there's no need to write code to generate an API, it is now much easier to enforce API standards across the company. And with observability built in, we have standardized when alerts are triggered. On the left here, we can see Gateway 1.0 that incorporated various domains. And on the right is the system after migrating to Gateway 2.0 that helped us establish clear abstractions. Gateway 1.0 was a single monolith where hundreds of engineers contributed. There was little to no separation between API and domain logic. Gateway 2.0 formed clear abstractions on the ownership of API and domain logic. As the company grew, this helped the teams build fast and in parallel without being dependent on a centralized team for code reviews. Each team now owns their own product layer that determines logic specific to that line of business. This also helps us isolate on issues and reduce the blast radius of potential outages. As we saw before, Gateway 1.0 was a monolith with many functions and a single-threaded Node.js service. By rewriting this in Go, we were extra careful about building for scale and performance. With Gateway 2.0, we saw that we could serve 10x more requests per second per core. One of the reasons for this was Go being highly performant as compared to the Node.js runtime for our use case. We also saw 2x latency improvement across the board, translating into significant business value. The chart above shows an Eats API that would earlier take 22 seconds at P99, and Gateway 2.0, it only takes about 4 seconds. On average, this helped us save about 15,000 CPU cores, and it's on track to recover an additional 15,000 CPU cores by the end of 2020, directly translating into reduced costs in maintaining the gateway. Uncaught errors in an API are bad, but they don't affect other APIs' reliability or availability, unlike the previous runtime we discussed earlier. Also, the various platform features, such as rate limiting, timeouts and retries, circuit breaking, prevent cascading failures from the backend. Overall, Gateway 2.0 helped us improve our reliability and availability to meet the 99.99% uptime. Our developers certainly feel great about this new platform. Now, let's look at how we can leverage this platform to unlock more value in the future. As we mentioned earlier, all of Uber's mobile traffic is served by this new gateway layer. Adding support for changing the communication layer to gRPC will become easy by just updating the gateway to support gRPC, while backend services can continue to maintain their current RPC mechanisms. We also implemented protobuf serialization based on the existing Thrift IDL. This is done on existing APIs and did not require any product change. Since the pipeline between mobile to the API gateway is tightly controlled and owned by the platform teams, this is entirely agnostic to the product teams. Moving to protobuf serialization reduced our payload size by up to 60% and decreased app latency by 30%. In future, we can add features to ban fraudulent users based on heuristics that are available in the gateway layer. We can also unlock a lot of value by providing product teams with a unified dashboard to monitor their business performance, providing rider funnels, and then use machine learning to improve user experience by pushing data to the apps faster. That was all of our discussion on Uber's API gateways and its evolution. In this section, let us see the things we learned as part of doing this migration from Gateway 1.0 to Gateway 2.0 over the last 18 months. These are general learnings that we believe can be applied more widely in the industry. Feature parity versus onboarding product teams. This is a very interesting challenge. When you build a new system, do you bring the new system in 100% feature parity with the old system, or do you start onboarding product teams and build the system along with that? Both these approaches work well in different scenarios. In our case, it was important to demonstrate that the platform works and is beneficial to the company. At the same time, it was going to take a huge undertaking to reach feature parity with Gateway 1.0 because it was built over a period of 5 years. So we chose to onboard a small set of product teams that depend on limited feature set before we achieved 100% feature parity with the old system. Onboarding product teams helped us cut our tech debt faster, since the new technology was already being built on the new stack. One very challenging aspect of this approach is that while onboarding teams to the new platform, we were also trying to achieve feature parity with the old system. This led to a balancing act between working on features and also supporting the new teams that was onboarding. Centralized versus decentralized migration. This is an important question to answer in every migration at this scale. Should we go with one team who would migrate all the APIs for the company, or should we decentralize the migration and assign them to individual product teams? In our case, since each endpoint had domain logic, it was going to be difficult for a centralized team to understand what is involved for migration. So we chose to go ahead with the decentralized plan for migration, backed by a company-wide mandate. The drawback of decentralized migration is that it takes longer, but it's a more scalable, and teams can do it at their own pace. Keeping momentum is hard, especially in a large-scale migration that can span multiple months. In order to keep momentum, it is important to track progress, share it with the stakeholders, so that the teams are aware of the benefits of moving to the new platform. It's also very important to celebrate wins and milestones to keep the team motivated and ready to go for the next milestone. In every migration, your tail end will look very different from the other 90%. This brings an enormous challenge in terms of planning for the tail end. Sometimes it might be better to leave the tail end in the old platform and let it reach its end of life organically. Other times, it might be worth to move to the tail end to the new platform. Depending on your approach, we would say that the tail end traffic would look very different, and the challenges it will bring will be very different from the rest of the 90%. Knowing this, prioritize your focus and effort in starting with what's going to be the most important and impactful. Finally, never do migrations. Just kidding. That's an overstatement. What we mean by that is that every migration should be considered along with its pros and cons. There are engineering costs involved in migrations, especially at this scale, that need to be weighed against its potential benefits. In some cases, you would find that building the new stack without migration might be more beneficial. In our case, the challenges from Gateway 1.0 were significant enough that they were getting in the way of growth and productivity of the company. To summarize, these are our learnings from moving to Gateway 2.0. Overall, this effort helped us move to a brand new Go stack that is bringing in amazing wins with developer velocity as the company grows. I'll leave this here for a minute so that you can read through these. Thank you all for listening to this talk. This is the last 2 years of work by an amazing API platform team at Uber. We want to thank the entire team that has contributed to this effort. Additionally, I would like to thank the GoLab organizers who have been an amazing partner in helping us put this together. Our contact information is here. If you'd like to talk more, please feel free to reach out to us. We will now open for questions.
All right, welcome back, everyone. We are ready now to go live with Tejaswi and Rohit to answer any and all questions you have. So let's go ahead and bring them on. All right, Tejaswi, I will turn on yours. And Rohit as well. Let's bring you all on. Hello.
Hi, everyone.
Hello. Hi, you guys. Welcome. So good to have you here.
Yes, it's great to be here.
Yeah. I want to say, first of all, thanks for your contribution to GoLab. You know, even though this year we are having it virtually, we are still very happy you could be with us. So before we go to the questions, do either of you have anything you wanted to say about your participation in GoLab?
It has been all the organizers have been really helpful, right? And every time I've had questions or issues, I got response very quick. So that has been great, and it's been great to be part of this community, learning along the way also from other talks and everything. So overall, very happy to be here, and I'm glad I'm participating.
Fantastic. Well, thank you for that, Rohit. Okay, Tejaswi, if you had anything to add?
Yeah, I'll echo what Rohit said. It's been great. It's the first time we're doing this virtually, so it's definitely new. But looking forward to Q&A and yeah.
Fantastic. Thank you. Yeah, it's all a little strange this time having it virtual. We all are experiencing some difficulties in the process. All right, let's go ahead and get started with the questions here. The first one we have is, what was the hardest thing about the migration to the new platform?
Yeah, I'll take this one. As we saw during the talk, our old service was written in Go, right? And over the years, around over 1,000 program engineers had contributed to it. So there was not a whole lot of uniformity. And we had a framework on, the runtime aspect of it, like how this is how you write your handler, this is how request response object works, and deserialization, etc. But when it came to writing their domain logic, it was like free for all. So when we were migrating to this new platform, this was going to be all code generated. So now imagine like 1,000 little snowflakes and trying to have one platform that is opinionated and tries to conform all of this into a single uniform gateway layer. That was the hardest challenge. But there were other concerns like the scale of the migration itself, in the sense with the number of people that were going to be involved, as well as having to support that while also maintaining a functional gateway that is serving all of this traffic. And there were like real big consequences if anything went wrong. So yeah, Tejasvi, if you have anything to add.
Yeah, I think that that covers most of the points. Like the migration itself, doing it safely and securely without causing any production outages at that scale was one of the biggest challenges. So the automated shadow framework helped to sort of reduce some of those challenges and help for safe migration. So those were some big challenges and around scale and velocity of the migration itself.
Mm-hmm. I see. Thank you for that. All right, let's go to the next one here, which is what about the tools for automating the migration, excuse me. Did you consider building some of those tools?
Yeah, so that was definitely an important consideration because, like, as we saw, this was a decentralized migration. So before we decided that it should be decentralized migration, we considered like trying to automate as much of it possible. But like I mentioned before, there was like in the gateway itself, there was a lot of domain logic that was written, and sometimes people did not even have their own backend services. They would just write all of their domain logic to handle a API request in the gateway itself. So this was not just a migration of the API layer, but it was re-architecting what our layers are going to look like. So the gateway layer was going to be thin. It was the one that was responsible for receiving the request from mobile and do some of the rudimentary things that would be common across all of the API requests. And then the rest of the domain logic was for the domain owner to move that elsewhere. So we couldn't have done all of that in an automated fashion very easily. And like I mentioned previously, there was also no uniformity as such in how this domain logic was written. So it was going to be basically a framework that would have to handle over 1,000 different cases and then try to automate. So which was just not feasible at this scale. What do you think, Tejasvi?
Yeah, I think automating things at the platform level by the platform team was definitely hard because of all the different scenarios possible in the old gateway. But at the same time, there were some product teams which did some automation. So we have a wonderful, Uber Eats team who sort of went through the use cases which are specific to that particular product. And then said, can we build some kind of automation which can just apply to these set of products? And doing that helped, at a certain level to sort of move things fast and automate that part of the process. But as a platform team, we did not build any automation just because of the number of different scenarios possible for the migration, and also different product teams wanting to do it differently and at their own pace, and yeah.
Sounds about right. It would be like a juggling act if too many things are involved with that, right?
Yeah.
Yes.
Very much so. All right, going on to our next question, which is what were some of the challenges or caveats with the use of Go in the project?
Yeah, so I can talk about that one. So one of the challenges we faced was around scale. So as we reached more and more endpoints over 1,400, 1,500 endpoints, So we were using EasyJSON, which is a fast serializer and deserializer for request response objects, which uses code generation. But at a certain scale, our build times were significantly high just because of all the code generation and the steps involved in building an endpoint, right? Which was affecting the overall goals of developer velocity. So we had to think about how can we, make builds faster and at the same time improve developer velocity. So we migrated from using EasyJSON, which is fast code generated serializer and deserializers to JSON IDER, which still gives us some of the performance benefits of being extremely fast, but at the same time it relies on runtime reflection. So it does not do some of the code generation, which was one of our bottlenecks in build times. So those were some of the challenges, just with scale. But other than that, Go building this in Go has not, has been wonderful for us. Rohit, would you like to add any more?
Yeah, I think around what you said for EasyJSON, that was definitely a challenge. Another thing I want to mention is the lack of reflection, lack of generics made it slightly difficult for us as a platform developer, because we are writing like code generation frameworks, and we are trying to then we have handling for all the various number types separately, whereas if we had generics, that would have made it a little bit easier. But that's a side caveat, and that was not a very big deal in our use cases. It's definitely not a blocker in any way. Just certain things were a little more tedious than they could have been. Yeah.
Great. Thank you for that explanation. All right. I don't see any other questions from the chat. So in that case, really quickly, if there's anything else you'd like to add to any of that, I'll give you a moment to do that.
Yeah, Rohit, is there something you'd like to add? Questions, we're happy to take them.
Sure. If not, that's fine. We can definitely end early. It's up to you guys.
Yeah, I mean, definitely, using Go has made us a lot more productive. And, as the company was moving from Node.js to Go as a standard, it was becoming a lot harder to maintain a Node.js service. And as the company kept growing, the number of new engineers in the company was always, that number was bigger than the number of people who have been here and used to Node.js. So then for every new engineer, it was a lot of productivity loss to for just this one service to figure out how the runtime works, and all the custom framework we had for writing HTTP request response, all of those. It has definitely saved us a lot of pain, as well as is helping us move forward faster. If I had to do it again, I think we would still choose Go and make almost all of the similar big decisions.
Yep.
Fantastic. Well, thank you guys so much for both of your insight. It's always interesting to see, taking a deep dive and looking into the inner workings of such a big company like Uber. So we appreciate that. And hopefully next year we'll see how it goes. But let's see. Let's have our fingers crossed with maybe next year's edition to see if we can do it live next time. But in any case, we hope to have you here for the next one.
That sounds
absolutely
great. Yeah.
And thank you so much for having us here today. It has been great.
Yeah, it's been a pleasure. All right, you guys, we'll see you around, and stay tuned. Thank you so much.
Thanks.
Bye-bye.
All right. Bye-bye.
Bye.
Okay, you guys, so we have a few more talks of the day. And really quickly before I mention the next one, you can definitely, if you liked the talk, you can go on the agenda page of GoLab and rate it. Definitely giving some feedback. We always appreciate that to hear from you all. So in about 20 minutes, we'll have our next talk of the day, which is data engineering in the Go shop with Mariah Peterson. If you were here for the Q&A yesterday, you'll remember that name. So hope to see you all there. Thank you.